So I'm Jesse Millwood. I'm part of DornerWorks. I'm an embedded engineer in their advanced embedded platform group. And so we kind of focus on hypervisors and secure embedded stuff like that. We're going to be going through a couple little mini tutorials here. So we're going to first go through a little bit of seL4 introduction and what that's about. And then we're going to use the seL4 test application, which is really great for making sure that your platform has everything that seL4 really needs to run. And then we're going to kind of zoom out a little bit and use Camkes to architect a little bit more of a complex system. And then in each of these, we're going to use Renode to emulate what we build. So why might you want to use seL4? Well, one, it's a microkernel. It's small. It's fast. It's backed by formal methods, so it's bug-free. It's rock solid for having in one of your more trusted areas of your system. It's open source and it focuses on security. So the microkernel architecture, it pushes a lot of that OS logic, any of your drivers, everything like that, into user space. And that's kind of the Wikipedia diagram there. It's really common for depicting this. Really, its main responsibilities, though, is enforcing the flow control, enforcing separation and access control, and taking care of your scheduling. Everything else is taken care of in user space. So, and it is important to note here that it does require it requires an MMU. So you really have to make sure that the RISC-V core you're using can provide that. So yeah, seL4 is it's proved correct, and this really means that there are no overflows, there's no deadlocks. The IPC fast path gives the same result as regular IPC, which really helps speed up seL4 when compared to a lot of other microkernels or really any other kernels. It has proven isolation, which is really important for breaking up your system and making sure that you can have really highly secure things running on the same board or platform as a little bit less secure things. It uses capabilities for the access control, so that really gives you a very granular ability to grant access to different threads and execution environments. And it has a proven information flow, so you can set up communication paths and be absolutely sure that there is not going to be any snooping. There isn't going to be any way that another maybe rogue part of your system can see what else is going on between other threads. And if you saw Granat's talk, he had a much nicer graphic, but the refinement proofs really show that the C code implements only what's specified in the higher level models, and this all carries down into the binary. And then I just have this note here that the proofs, the bug-free nature of seL4 doesn't really, it doesn't extend into user space, so you still have to write secure code in your user applications, but you can at least be very sure that any buggy code in user space is going to be isolated, so you can do design around that. So I really wanted to highlight the importance of seL4 being open source. It's been it's really a gem of software that we have access to. It's the culmination of a massive undertaking. Total, it took about 20 person years to complete the kernel development and the reusable proof frameworks, 11 and a half of which were really just the design, implementation, and verification of the kernel. It is GPL'd, but a lot of the Data61's user space libraries are a mix of MIT, BSD, and GPL. And there isn't any dynamic linking you have to really, it's not really provided out of the box. I mean, I guess it's theoretically possible, but everything is highly isolated, and you really have a lot of static execution environments running. And DornerWorks has a few blog posts about like why this really means a lot to us, but it's really been nice because there's been several drivers we've developed that or code that we've worked with that we've pushed up and worked with Data61 in the open on GitHub, and it's really just improved the quality of the code that ends up being available for everyone to use. So what do we mean when I say that seL4 is secure? It really achieves this by using the capabilities to determine access control, and mainly this is with objects that the kernel can understand. So everything kind of starts out as untyped memory, and then it through system calls that you kind of mark it as V spaces, which is the virtual memory, C spaces, which is the directed graph structure that threads keep the capabilities that they know about. There's IPC and endpoints, which are just messaging objects, and then threads kind of wrap it all up, and that's really the execution environment. So when something wants to access a resource or an object, it really needs capability, to that object, and the kernel manages all that. So you can't fake it out. You can't do anything that you haven't really been granted access to do by somebody else. So all this really sounds great. What can you use seL4 for? You're not going to be able to use it out of the box. It's not like a desktop OS. You're not going to be able to check your emails, do things like that. There are some projects that there's one UXRT, I think they were trying to make some sort of general purpose OS on top of seL4. Renode, they have a way of using seL4 as the underlying microkernel, but really where it shines is making these highly secure static embedded systems, which is really great for, you design it at build time, you make sure your capabilities, all your access control is taken care of, and then that it's going to boot up that way every time. I also made the note that there's no POSIX really available. When seL4 was designed, it didn't really let itself be kind of hampered by some of these other interfaces. So there are the C libraries and things like that, and it's possible to implement certain subsets in user space if you really want to. So when you are building a seL4-based system, there's a few architecture that you might want to consider. You can always start off with the seL4 just really bare applications, and there's Data61 provides some libraries that you can use that are kind of wrap around the underlying seL4 API, and that really will require you to really think about creating your capabilities, creating all your threads, and your root thread, kind of building up your own infrastructure for managing all that. You can use architecture description languages like Camkes, where it allows you to define things in a little bit higher level language, and then you rely on some generation, but it really allows you to focus on your business logic. I put hypervisors there, and I think we all know the RISC-V hypervisor mode really isn't, it's not ratified or ready, but we do use it on ARM quite a bit, in x86. So we're really looking forward to having some platforms in the future that, hopefully in the near future, that enable that. And for what it's worth, we've done some benchmarking with seL4 as a hypervisor on ARM and compared it to just running natively, and we've got some pretty impressive results from that. So if you're interested, we can talk about that later. Some other interesting tools here is Cogent, which I believe is another Data61 language that allows you to write in a higher level language, but then it generates your C code and Isabelle code, so you can kind of prove out your program that way. And then there is some Camkes. There's some ways that you can use rump kernels, the NetBSD drivers, wrapped up in an isolated environment in Camkes and in the bare kind of seL4 applications. All right, so we're going to start off with just kind of how to build a system. We're going to start with seL4 test, like I talked about before. This is really great for new platforms. It's really been an indispensable tool when we've ported to new platforms. It makes sure that your seL4 knows about your memory. It makes sure that everything's configured properly, and it really helps too to get familiar with the surrounding tools and the project layout. So it doesn't matter if you don't really have hardware. There's plenty of emulation tools out there. We're going to be focusing on Renode, which it aims to be able to run the same binary as the hardware. And some of the 64-bit RISC-V CPUs that Renode does support is the Microchip PolarFire SoC and the Sci-5 FU540. We're going to be focusing on the FU540 because we're just going to use the Hi5 emulated board. So to set up your environment, you can, that first link there, you can set up your host dependencies if you want, but Data61 also provides a Docker environment, which is really, really nice. It bundles up all of the tool chains. It bundles up all of there's some Python libraries, there's Haskell, there's a whole lot of tools to get right and get in the right version and everything. So I usually just recommend doing that. And then there's the Google repo tool. So that is used for pulling down manifests and making sure that your project contains all of the right Git repos at the right revisions and everything like that. And we'll go through how to use that. And there's, later we're going to be using Renode, but it requires some mono runtime libraries. And then you can just download I believe they have the deb packages at their GitHub release page. Then we will be using this a little bit later too, but there's the robot testing framework that kind of hooks into Renode, and that just requires some other host Python libraries. And usually I install Renode outside of my Docker container because it needs X to run, and if you didn't create your Docker container by sharing all your X stuff with it, then it just doesn't work that well. So this is really all it's needed to get the code. This is where the manifest repository is. So you have right here is the manifest URL, and with repo you can actually you can just point it to a local file too if you just want to develop on your own system. And then this is the manifest at that repository that we want to pull down. So I just named it seL4 test, and then that is going to just initialize your project directory, and then repo sync will pull down everything. And we'll see that here. This is just a quick GIF of just kind of going through what it looks like, just so you know you're maybe on the right track. That one is just running the init, and then as you can see, after you run sync it. You can see all your branches and repositories come down. If there's a problem, it'll break out there and tell you that one of your branch doesn't exist, or there's malformed XML, something like that. And you can just fix it. But this pulls everything down into a project structure that's defined by the XML. So this is just a snippet of the manifest file on the left side. And as you can see, you can specify different remotes. And then the main part here are the different project elements. And then each of them have XML attributes. So the name would just be prepended or just be tacked on to the end of the remote URL that is associated with. And then the path is just where you're going to put it in your project layout. So by convention, this is how most of the Data61 projects work. You have a lot of the projects go into the projects directory. Kernel is in the top level there, and then tools contains some other tools. Now I've added the Docker files, Data61's Docker repo to this, so that everything's just all contained in one repo. So if you want to do this later, you can. And I've also included some other helper scripts that I just put in seL4 extra there, and we're going to be using those. The nice thing here is you can symbolically link files to the root of your project directory here. So a lot of these run scripts in the start container are just in my extra scripts I added there. And they're really just wrapping a lot of things that are already there. But I also want to mention here too that it's really important to start from a known manifest, because as you can see, there's a lot of revisions specified here, and sometimes it's a little hard to make sure that all of your repos, all of these moving parts are all synced up and at a working spot. So then at this point, we have the code all pulled down. We have our project structure all set up. So then if you are using the Docker environment, I usually just have a terminal open and just enter it here. I have my start container script here. We'll use the Docker files that are pulled in and just build the container and enter it right there. By default, the make target that's used to start that Docker container up doesn't pull in the RISC-V tools. So if you want to look at that start container script and see the actual incantation to get that going, you can. But this is all just set up for you to use. So this is just another GIF of just going through it. I'm just kind of showing that it mounts your project directory right there at the first directory that you're going to see when you're in your Docker container. So I'm just kind of showing the same files are there. But this really lets you do all your builds in one area there, and then you can still use whatever text editor or other tools you want outside of that environment. All right, so now we've got the code, we've got our build environment up and going, and now we just need to really just configure the build. So they use CMake for all of the projects and libraries in the kernel. And most of the time you would just use that init build script that Data61 uses and links into the root of your project. And that really just, it does some kind of boilerplate CMake stuff, and then there's a little bit extra logic there to determine what the kind of the core application is for your project. So when you call init build, you can then just kind of tack on all of the other CMake variables to further configure things like your platform, things like that. If you want to kind of dig down in there and see what other knobs and levers you have for configuring things, usually I kind of just go through, find the CMake lists.txt for the different libraries, and then usually there's settings.cmake and easysettings.cmake, which really kind of have the variables in there that are meant to be changed, more or less. There's also the CCMake tool, which I just learned about the other day, which is kind of neat. It's a ncurses interface to CMake, so it lists all your variables out there too. And since this is a out of tree build, you have to make your build directory, cd in there, and then run the init build script from there. And once that's all that configuration is done, you just simply have to run Ninja, and it will it'll build and compile everything for you. So usually that gets a little old, so for me, I usually just write a script to do that for me, and I've included that as that run build script. So you don't have to make the build directory, it does that for you. You can just do the run build, and here are the CMake variables that I've set in there. And so some of the main ones are the platform you're going to use. That is a key one that sets up a lot of things for the kernel, libraries, your application code. I usually just define the cross-compiler prefix kind of out of habit, but it usually gets set from the platform. Let's see. So this lib seL4 test print XML one, that's one that I'm just setting that is in the seL4 test application, and that's just so that it prints out XML, which is a little bit more machine parsable, and we're going to kind of show how that can be used with Renode and Robot in a little bit. So this is just another GIF of it running. It's just kind of so you can make sure that everything's working well. This is it's going through the CMake stuff right now. I print off the variables kind of in between CMake and Ninja there, and then it's just kind of going through the Ninja build right now. And then it will put your binary in the images directory inside your build directory. So yeah, it doesn't take too long. It's pretty quick. It uses the Berkeley bootloader BBL right now, so it builds that all up for you, packages up. Okay, so now we're going to move on to using Renode. So with Renode, I usually use the monitor scripts so that I can set up the platform and point it to my seL4 binary, and then you just have to make sure you point it to your platform's DTB, which is what gets passed into your bootloader. This is just the monitor script that I use. It's pretty simple here. Some of the main things are, here's the binary, the DTB. Those are just getting set to some variables there. It's important to remember the at symbol in the Renode scripts for setting up or for indicating a path. And you can see, as you can see here, this is just a relative path to the correct places in the build directory, or the project directory. And then we're using the Sci5 FU540 here, and I've just included it here in the tools that I've brought in with repo, because I had to make the memory a little bit bigger, so I had to edit that in the REPL file and then in the DTS too. So then this show analyzer UART is just going to pop up a kind of a emulated serial terminal, and then this is where it's getting loaded into the system here. So the load ELF, it's an ELF, so it knows where to go. And the FDT gets loaded in at that address. And like I mentioned, I had to edit the REPL script, And this is, I think it kind of shows kind of some of the power of Renode here, is that it uses this declarative, these declarative files where you can really easily see what your system is made out of and how things kind of plumb together. And it's pretty easy to just kind of edit it and then reload everything. You don't have to recompile anything. So yeah. All right, so now we're going to just run the code that we just compiled. So you really just have to run Renode and then just pass it your script. And just one caveat here is that there was a small kernel modification needed that is included in the kernel that gets pulled in repo. Renode was just having some problems with when sfence is called and given arguments. So I just took the arguments out and it ran just fine. So this is just another GIF of Renode running. I have the run Renode script, so if you just call that, it'll pull everything in and run it. So on the left there is the monitor, and on the right is that show analyzer, the UART. And as you can see, it just now it would go for a lot longer, but the GIF just keeps going, looping here. But I can't pause it, so you can kind of see the boot up, and then it enters into the seL4 test application right there. Now at the end, it'll run for a while. I think it ran for a couple hours to get through all the tests for me on Renode, which is a little bit. But at the end, everything passed. If it doesn't say fail, but all is well in the universe is it's a very welcome thing to see, especially if you've been trying to port something to get it to run, for a couple weeks, and then you finally get that. It's just it's a nice validation. So I want to talk about a little bit about some of the other Renode features. Like I said, the declarative syntax is really nice. Not only for specifying boards and SOCs, but you can define more complex connected environments as well. You can define RF connections, Ethernet. This really means, like I said before, that there isn't any recompilation needed really for adding in extra features to your system. It supports heterogeneous systems, so you can have multiple architectures running in the same emulated environment. It provides different scripting interfaces like Python scripting, the Renode monitor scripts like we saw, robot scripts, robot framework test scripts. Now it's not cycle accurate, but it also doesn't do kind of that like on-the-fly translation to your host architecture either. It is really kind of instruction by instruction. So it uses virtual time to kind of make sure that everything is synced up across all of your kind of emulated cores and emulated devices. So, like I said, it has networking support, it's pretty cool. It allows you to set up virtual networks or taps really easy from the monitor. So if that interests you, you should really check it out. And you can write your peripherals in C# and actually just then include that at runtime, so you don't have to recompile everything if you're even adding in custom peripherals too. So I thought that was kind of cool. So now we've built everything, we've emulated it a little bit, made sure that it works, and now it's kind of a good idea to make sure that things work in the future. So with the robot framework, it might be a nice thing to have in like your CI, your continuous integration system. So it's really good for acceptance-based testing, where you have kind of an input, you expect an output, you check it, kind of move on like that. And because there's the Renode integration, you can call the monitor commands in your tests, which means that you can let things run for a little bit. You can pause everything. You can check, peek and poke at memory locations, all from this automated test environment. So this is the first snippet of my robot test framework script, which it gets called with run robot script that I have symlinked into the root of the project directory. So if you notice, this is really just the same as the beginning here is just the same as the Renode monitor script that I had before, but it's just kind of in this prepare machine block. Then it allows you to write some of these test cases. So I have the boot test case, and that some of the main parts here is that I make sure that this is a requirement, that it sees the BBL bootloader text on the UART there, and then I make sure that it sees the ELF loader started. So then I can say, okay, I think that that's enough for me right now. I can say that it's booted fine. I say that it provides this, which means that other things can require it, so you can kind of chain together some different testing dependencies. And then this is just a really simple one, but I just wait for this test to kind of be printed out. If that doesn't get printed out exactly like that, then it'll fail, and you'll see that. Oops. So I didn't have a GIF for this. It was pretty short output. It'll just go through and tell you if things passed or failed. But a really nice interface that it shows is some HTML outputs that. So it has this report, which lets you kind of just see some really high-level information, how long things took, which actually was kind of nice on another project we had. One of our tests was taking a really long time, and it kind of everything compiled, everything ran, but we kind of saw that there was some weird things going on. It kind of led us to kind of a corner case bug that we found. So it was pretty helpful there. And then this is the last one was the report. This is the log, and it lets you kind of drill down, expand and see some more information for the tests. All right, so that was all kind of a simple, more simple application, and now if we want to move on to some more complex systems, I'm going to show you how to use Camkes a little bit, and I think really where this shines is that as the systems get more complicated, there's a lot more resources to keep track of, and especially in seL4 when you have more resources, more threads running, and you want access to be granted in certain ways. There's a lot more capabilities to keep track of. There's a lot more kind of boilerplate things that you have to do manually, and Camkes really takes care of all that for you. So the manuals at that URL, if you're interested, it goes through all the keywords. There's examples. It's pretty in depth. So some of the other features that it provides RPC interfaces, which kind of deep down, really what that does is you have your application. If you want to have two threads connected, it'll spawn off threads to kind of wait on blocking system calls, and that's just areas where manually bugs can kind of introduce in your application code there, I think. So, and then some of the other really important things is that it calculates all the capabilities you need and makes sure those are all kind of doled out in a proper way. So this is going to be a really similar process that we did before, where you make your project directory and then run repo init in there. And so as you can see, this is the same URL, but it's just a different manifest file. And then you run repo sync, and it pulls it all in. And we'll see this in a little bit, but really what and I said start from a known working system. Well, I'm starting from the Data61 Camkes application examples. So I just kind of added my own application in there, and I could be pretty certain that everything else, the libraries are at the right revision, kernel, and everything like that. And just another note about the Docker environment that, by default, if you just ran make, the default make command for it, it wouldn't pull in all the Camkes stuff either. So the start container script that I include here, it'll pull in the Camkes stuff and the RISC-V stuff for you. So if you're interested in what that is, you can look at that. So this is the project layout. It's a little bit different. You can see that it pulls in the Camkes tool. This is the project that I was talking about, the Camkes kind of demo applications. These are, the symlinks are all pretty much the same. There's some, the global components is another Data61 project that has their Camkes components, so a lot of things to kind of build off of and reuse. And there's just some other tools that get pulled in there too. So I want to just kind of drill down into we're at the projects, Camkes, and then there's the apps. And so I said I added my own kind of simple serial application. And this is really just the general layout of application. You would have your CMake lists.txt file at the beginning there, and then by convention there's usually a components directory where you have your kind of your business logic, your C code that really has access to when Camkes runs, it makes all of the structures that it generates and builds for you available for you to use. So then you would have this kind of root Camkes file that takes care of really architecting your system. And we'll look more at that in a second. So the application I added is just this serial application, and it sounds trivial. It sounds pretty easy, and it would be if it was all just running in the same address space, but it isn't. We're going to take advantage of the isolation and the communication paths that seL4 makes available to us. So we're going to be using several different servers, and which are like just the drivers, some reusable components, and making sure everything is connected in there. But I think it really kind of shows the stuff you have to look out for, and makes it a little bit more instructive of like how you would build up your own system. So like I said, every Camkes application has a root Camkes file, and this is responsible for defining the architecture of the whole system. So it's responsible for instantiating all of your components. It's responsible for connecting all of your components up with RPC calls and shared memory. And then a lot of the components have different configuration. Depending on how you write it, you can have different configuration variables that you can set up, make things a little bit more reusable and kind of dynamic. So this is that. This is that root Camkes file, which they all have the assembly block, which contains the composition and configuration. So the instantiation all occurs here in the composition block, where I've got 3 components here. I have my serial application, the serial server, so it's just called serial, and then the time server, which is just called the time server. So these are the different connections, and there's a lot of different types of connections, and they are mainly generated. Camkes uses the Jinja, J-I-N-J-A templating framework to template C code. So which is kind of nice because you can actually set breakpoints when you're building to kind of see what your templating engine sees at that point. So it's kind of nice for development. One of the RPC connections I want you to look at, though, is this serial client one, and we're going to be digging down into this a little bit later. But we have the component, and then this put char interface, and then we're connecting it to this interface of the server. So this is just a diagram of kind of what this looks like. We have the application, like I was talking about. There are some endpoints for sending small amounts of information. There's some RPC connections so that my application can ask the serial server to do certain things. And then there's a shared buffer, which is kind of how the information gets back from the serial server to the application. Now what's really nice here is that all of these components, they are running in their own execution environment, and it's taking advantage of that isolation that we were talking about before. So if my application kind of went rogue, there was a buffer overflow, and was trying to execute shellcode, there's no way that it can access the serial server. There's no way it can access the hardware because I haven't given it the capability to do so. I've only given the serial server the capability to the UART device and the UART interrupt. And the same goes for either one of these drivers. They can only communicate with each other over these well-defined interfaces. And like we talked about before, the time server has no idea what's happening over here. It just simply can't, and it's proven. So we're going to start off with the serial application. So this is just a simple definition of the component that we're using. The control keyword here is important because it means that this component is going to have an entry function, which is just called run here. So then you just have to make sure that you provide that in your C code, in your your business logic. Now here's where that uses put char, and so there's the put char interface that we saw was connected to the serial server. So this is the keyword that says that this is going to be a procedure interface. So this is the type, and then this is the name of it. It's pretty. Then the emits and consumes just means that there are notifications that it emits, and then there's notifications that it consumes here. So now going to the serial server, this is just a snippet. I just wanted to kind of show how things connect up. This also has a control keyword. Now, if you didn't have that control keyword, it would it'd be more of a event-driven component, which maybe it just provides RPC functions to use. Maybe it just waits on certain notifications or something like that. Now, see, this one has the same put char interface type, but it provides it. So that's an important part of the RPC calls. There has to be a user and there has to be a provider. And this one is just called the process put char. So that's what allows us to connect those two together. And this serial server has the timer procedure interface. So if you were writing an application, you said, okay, yeah, I want to use the serial server. Well, you'd want to go and look at the Camkes component file and see what does it need, what does it use. So then you would have to kind of go and find the components that provide that and make sure that those are all connected at your root in your root file there. So yeah, this is just kind of the rules of thumb for the using the RPC interface. You have to have at least one component that provides the interface and at least one component that uses it. So this is that this is the definition of that procedure type. So that was that the middle the middle part of you have the uses, and then this is what you would put there, the put char, and then you would name it for that component, the local name. So these are just, there's only one function that it has, but you could have multiple ones. So the component that provides it has to make sure that it implements that in its kind of that business logic in the C file. And then the user can just simply call it, and then all of that RPC logic is all taken care of for you, kind of behind the scenes. So what does that look like in the C file? You have the procedure interface name. So we in the provider, the serial server, we said that it was called process put char. So you just have that here, and then the underscore, and then that function name that it's implementing for that interface. And here you can just see that it's expecting an integer, and really it's just handing it off to some other internal functionality. So on the other side, the user of that interface, you would this is just a very naive way of just calling this over a string. But we have the and I probably should have named it differently, but the interface instance name, which was that put char. So you had the uses, the type of that, which was capital P put char, and then put char here, underscore, and then the function name. So you don't really have to know how it's implemented or what it's named from the component. You just have to know how it's named for your local the component that you're interested in, you're writing. So why don't we've done some trainings with people, and they say, well, why would I want to use Camkes? I don't trust the generated code. There's too much indirection. But really, one of the key things that it does here is that capability calculation. Now, you saw that 3 components really wasn't doing a whole lot, but there's roughly 1,000 capabilities that you would have to take care of manually, and that is it's a huge headache. There's a lot of places it can go wrong, and there's a lot of places that maybe you give a capability or something like that to something that really just doesn't need it. So you kind of introduce some vulnerabilities, I think. But with Camkes, it really makes sure that all of that framework is taken care of for you. And like I kind of said before, there are, with those like RPC calls, there are threads that are kind of spun off. There are things like that. That's kind of a framework that you would probably have to end up doing yourself anyways, which just kind of, unless you make sure that it's separated out from your project, it's probably going to end up kind of bit rotting anyways. But if you are interested in looking at what the capabilities are that are created, there's a CDL file, the capability description language file, that is in your build directory. All right, so we've kind of gone through writing the Camkes, all the Camkes code. We've connected everything up. So to configure the build, it's very similar to what we did before. So there's the platform, which is important. I'm telling it I want to use an ELF. And then this Camkes app CMake variable is required. And the way that it's used here is that you just have to set it equal to the directory name of your application. And this is unique to that. I said I'm working off of the Camkes example applications provided by Data61, and this variable is in, I think it's in the easysettings.cmake. So it's in one of those files that I said, you go look at those, see what the knobs and levers are to change, the ones that are kind of really meant to be changed. So that was in there. So yeah, running the build is exactly the same. You just do the run build script, or I provide that run build script. but it just kind of sets those CMake variables that we just talked about. This is just kind of a quick, this is just a GIF of it running. It's got a very similar output. You might see a few other things. You'll see kind of some CapDL invocations, some Camkes invocations. Here it's saying that it's generating 27 files. So you saw that I just had those couple components, but it really pulls in a lot of other things to make kind of a secure static system for you. And then it's going to just put it in the same directory, the same images. It's going to put that ELF file in that same images directory that I talked about before. And there's that CDL file. Yeah. So if we want to emulate it, we can. We can use that same platform that we're using with Renode. You just have to change the binary that it points to. Now this is taken care of by the files that I have included in the project. So really you just have to do the run Renode script. And that's here. Now this takes about a minute to run. You can kind of see there that you've got the BBL up at the top, and the ELF loader, which is the program that it extracts the seL4 kernel and the application code, puts it in the right locations, does a little bit of memory mapping things, and hands off execution to the kernel. So that's kind of telling you where everything is, the physical address to the virtual address mappings. It says that it's jumping to the kernel. This is some kernel printouts. And then now I've gotten to my application code. I'm just printing out so this is just kind of showing, I'm entering these characters and they're actually making the round trip. I'll show you. They're making the round trip here from the application through the RPC call to the serial server, and then the get chars coming up through the shared buffer. So it's kind of doing this whole round trip thing and using those defined interfaces that we kind of talked about. All right. So using seL4 in your projects, like I said, start from a manifest, get the build process correct. It's really nice to start from the seL4 test, make sure that you have your device trees correct, everything like that. It might be nice to set up a testing environment. I kind of showed you kind of how to do that with Renode and the robot scripts. Feel free to explore some other user space architecture systems. We haven't used Cogent or the rump kernels, but they have some really promising features that really help develop some secure static systems. There's a lot more to explore with Camkes. I really just scratched the surface there, but there's ways to get involved with it. You can join the community. There's the mailing list there. There's the two main GitHub projects, seL4 and then seL4 proj. There's a discourse group, so if you're not the mailing list type, you can use the forums there. There's plenty of other Data61 content. The tutorials are really nice. I didn't talk too much about capabilities because Camkes really kind of abstracts a lot of that away from you. But if you're interested in capabilities, run through the capabilities tutorial there. There's a lot of really good tutorials there. And then, in DornerWorks, we do a lot of system design and board bring up and training. So is there any questions? All right. Well, I do have 5 minutes, and I had a few extra slides, if anybody's interested. I kind of glossed over this, but when seL4 boots, it creates this root thread where it hands off all of the untyped memory and all of the, it hands off a structure for describing to the user space what the boot environment is, and Camkes kind of does this all for you. But it's kind of important to know that there is this root thread that does have basically access to everything. But Camkes, it's nice where Camkes, this is where Camkes gives out all of the capabilities and everything, and then I think it just kind of goes to sleep. So, which is important if you don't really want that to kind of persistently run in the background, because it does have access to everything. Yeah, usually it's responsible for creating virtual memory spaces, and you have to set up your own memory allocators and everything like that. This is kind of the boot process, where you have the DTS, or the DTB, I guess, gets passed into the bootloader. That hands it off to the ELF loader, and like I said, that's who's responsible for extracting things, putting it in the right memory locations. Hands it off to seL4, who does, it sets up its own memory space, and then everything for the root thread, and hands things off to the root thread, who then is responsible for creating all the other threads in your system. Yeah, and then this was just kind of a nice graphic for kind of showing where the ELF loader kind of puts the kernel and everything like that. So that's all I've got.